Hello students, in today's class we will start reading about the temperature dependence of resistivity. See, in previous class we have seen that resistivity is dependent upon two things. One is the material of the object under consideration and other one is temperature. So in the case of material, we have seen whether it's a conductor, semiconductor, or our insulator, it depends accordingly. Like in conductors, it have less resistivity than semiconductor and then insulator. And whereas when we see the case of temperature, how it varies is something we have to study and understand. So it is said that our resistivity is inversely proportional to the temperature. If temperature increases, resistivity decreases. What does it mean? It means that in case we are increasing the temperature, we are allowing more currents to flow. So in that case, what we exactly doing is that we are reducing the resisting power of that material. So first of all, resistivity of a material is found to be dependent upon temperature. Over a range of temperature that is not too large, the resistivity of a metallic conductor is approximately given by rho T equals to rho naught into 1 plus alpha T minus T naught. Here what does rho T alpha naught, rho naught, alpha, T and T naught implies? See, rho T is resistivity at a temperature T, whereas rho naught is the resistivity at a reference temperature T naught. What is a reference temperature? A reference temperature is a particular temperature we have taken to compare the resistivity at a different temperature. Now we have found our standard resistivity at temperature equals to 298 or 273 Kelvin. Now with respect to resistivity at this temperature, we aim at finding resistivity at higher or lower temperature. T naught will not always be higher or lower than rho T. It can be anything. Okay, the temperature we can measure at lower temperature as well as at higher temperature. So this is T naught. Over here is T, which can be anything lesser than 273 or anything more than 273. Then alpha. Over here is alpha. Alpha is the temperature coefficient of resistivity. Temperature coefficient of resistivity. Its dimension are temperature inverse and it's positive for metallic conductors. It is simply given if a alpha is there and in discussion we have metallic conductors, alpha is gonna be positive. Then we'll see the graph over here. So this graph number 1 is showing the property of our material. What is that material? That is copper. This is showing the relation between resistivity and temperature. In the case of material copper, here as the temperature is increasing, our resistivity is increasing in this manner. Basically, the units over here are taken in the range of 10 to the power minus 8 ohm meter. So when it is increasing, it will go to 10 to the power minus 9, 10 to the power minus 10 and so on. Okay. Second is graph number 2. In this case, our resistivity is in the range of micro ohm centimeter. So that resistivity is 10 to the power minus 6, in the range of minus 6, and it is versus the temperature. And this second graph is for a very good alloy, that is nichrome. We will be reading about the nichrome. So this graph depicts about the nichrome. Now, above relation implies that a graph of rho T plotted against T would be a straight line. At temperature much lower than 0 degree centigrade, the graph, however, deviates considerably from a straight line. If we are going below the 0 degree, we will not see any straight line graph. Now, above equation can be used approximately over a range which is limited for temperature capital T around any reference temperature T naught, where the graph can be approximately as a straight line. Now, nichrome, manganese, constant 10, these are the metals which exhibit very weak dependence of resistivity with temperature. If you are increasing the temperature, for these three metals, we will see that resistivity is quite constant. There is less changes in the case of resistivity. What is nichrome? Nichrome is a very famous alloy because of its less dependence on temperature for resistivity. It's an alloy made up of nickel, iron and chromium. Nickel, iron and chromium. Okay. This is also a very much important question with respect to your board and entrance exams. Now, we'll see the graph number 3 over here. This graph is a semiconductor graph. This is showing the relation between resistivity and temperature for a semiconductor. So as temperature is increasing for a semiconductor, the resistivity is decreasing. And it is decreasing in such a way that after a certain point, the amount of decrement is becoming lesser and lesser. Now, these materials thus used in wire bound standard resistors. Okay, so as these materials nichrome, manganese, constant 10 are not dependent upon temperature, at higher or lower temperature can give resistance value almost similar. They are used in the wire bound standard resistance. Why they are used? I'll write over here. Because at higher or lower temperature, these metals can give same value of resistance. Okay, since their resistance values would change very little with temperature. From above equation, resistivity of a material can be given as rho equals to 1 upon sigma. What does a sigma imply over here? Sigma is conductivity. Now, we will relate the rho with respect to our relaxation time, mass and number of electron. So, rho is given as m upon NE square tau. That is the relation. Now, tau depends inversely both on number of free electrons per unit volume and on the average time between the collision. This is the relation of resistivity with free electrons and average time. Unlike metals, the resistivity of a material semiconductor decreases with increasing temperature. Resistivity decreases with increasing temperature. As we increase temperature, average speed of electrons, which acts as the carriers of current, increases, resulting more frequent collisions. The average time of collision thus decreases with temperature. In a metal, N is not dependent on temperature to any appreciable extent, and thus the decrease in the value of tau with rise in temperature causes rho to increase as it is observed. What basically they are trying to say is that in a metal, this is our atom with these electrons. They are in a random to and fro motions. These electrons are in motion. When the temperature is increased, what exactly they show is the motion does not change too much. In case this electron is moving with a speed of 18 meter per second, it may move with 19 meter per second, but not more than that. So if we see over here, there is no considerable change. So our value of the resistance is not changing. The conductivity in such a case is same. Conductivity is same or almost constant. You can understand, if you are not understanding with respect to resistivity, you can understand the same concept in the case of conductivity. In conductivity, it is actually saying that the electron's motion helps in the conduction. Okay, I'll explain it better in a flowchart way so that you understand how our resistivity is increasing or decreasing in the case of semiconductors and conductors with respect to temperature. See, we have the three cases over here. One is our conductor, where conductance band and valence band coincide or overlap each other. Okay. Now other thing which we have is semiconductor. In this case, the conductor band and valence band have less energy gap, and in case of insulator, conductor and valence band have higher energy gap. Okay. Now, in the case of conductors, electrons show to and fro motion frequently. In this case, it is less predominant, and in this case we will see that there is almost nil or no motion. Okay, now the two concepts which are there in that, one is resistivity and other one is conductivity, and both are opposite of each other. Resistivity is resistance provided and conductivity is conductance. In case of conductors, conductivity is higher conductivity. Okay, so we have lesser resistivity because of to and fro motion of our electrons. Now we will see in semiconductor, conductivity is made higher by adding the impurity. So resistance is there, but both are in a normalized way. By adding, we can make our semiconductors conducting in nature. So some amount of conductivity is there and some amount of resistance is there. In case of insulator, lower is the conductance and higher is the resistance. Now when we see our conductors, electrons are showing to and fro motion. When temperature is increased, these electrons show more random collisions. So due to which what happened, rho equals to 1 upon sigma equals to m upon Ne square tau. Okay, so in this case our rho is inversely proportional with tau. Our tau, the time of collision, is increasing. Sorry, tau is decreasing. This is relaxation time. The time between two successive collision. Relaxation time between two successive collision. So this time is being in like decreased. Random collisions and faster collisions. Faster collisions. So as the collisions are faster, relaxation time is our decreasing. And it is doing what? It is increasing the resistivity. Initially resistivity was less and hence in this case resistivity is higher. Okay, so that's why our alpha is positive. Resistivity became higher, flow of current decreased, and hence the value of alpha is positive. Okay, similarly if we see the case of our semiconductors, hope you understand the mechanism in the conductors. Okay, I have proved it with respect to the formula we have seen previously. So if we see it with respect to the semiconductors, the Eg is lesser, energy gap is lesser in this case if the temperature is increased. Temperature increased, motion of electron is increased. Motion is increased, which causes higher kinetic energy. So this higher kinetic energy results in more motion of electrons from the valence band to the conduction band. Hence, more conductivity. So in the case of semiconductors, what happened? The ratio of conductance increased, then the rho, resistance. So temperature increased and resistivity decreased. Now if we see in the case of our insulators, what happens? In insulators, conduction band and valence band are far away. We provided a very high temperature. Electron present in valence band got energy and started jumping. But still Eg between conduction band and valence band is very high. So our electron cannot cross the energy gap. Hence, no conduction. Hence, in insulators, there is basically almost no flow of the charges. But in case the insulators are having quite lesser Eg, like what kind of example we can give is not the very insulators, but some ranges have this Eg gap quite lesser than the bigger ones. In this case, slight motion of electrons is observed and slight conductance is seen. So that is one thing. And in case of insulators, I would like to give an example of what comes to your brain whenever we see a insulator which is highly insulator. Though we are providing high temperature, we are trying to change its valence nature, we are trying to change its conductance nature. So the only best example which can give us a best understanding that comes to our mind is diamond. Diamond is an insulator. Though we provide high temperature, it doesn't show any conductance. So it is one of the best example of insulators under the different oriented conditions. So this is for the today's class. In this class we have read about the temperature dependence of resistivity and how in three different kinds of material it is showing the dependence. It is totally different. In metals, I'll summarize. In metals, what happens? Our rho decreases with increasing temperature, whereas in semiconductors and insulators, opposite happens. We increase the temperature to increase the resistance, to increase the conductance. Okay, make the change kindly. So that's all for today's class. We'll meet in the next class. Have a good day. Bye bye.